So the question that is in front of us is from the turning mechanism, right? Now you can see that we have a cylindrical body that is carrying a length of 100 mm and it has a diameter of 40 mm, which has to be reduced down to 34 mm for a length of 40 mm, and for the rest length of 60 mm the diameter has to be reduced down to 26. Now this is the case of step turning. It's not the case of through turning. We're not going to reduce the diameter along the entire length. Rather, we are going to reduce the diameter for a specific length, and then for another specific length the diameter will be different. What is to be the approach for solving this question? Let us understand. First of all, you need to realize that here we have the cutting speed. So if cutting speed is provided to you, if cutting speed is given to us, then we need to find out the value of n with the formula v cross 1000 divided by pi into d. Now, the velocity that is given to you in the question, it can be maximum, it can be average, but since nothing is specified, so you have to consider this velocity. As the average velocity. So this one is the average velocity. Now, when we consider this velocity as average, the diameter also has to be average. Now, what do you mean by average diameter? There is one diameter that is initial, which is 40 mm, and when depth of cut is introduced, so after the first pass, the final diameter has to be 40 minus twice of depth of cut. So 40 minus 2 into 3. So 40 minus 6, that will be 34 mm. So when you consider the velocity to be average, then the diameter also has to be average. And now what will be the average diameter? That will be 40 plus 34 divided by 2. So it has to be 37 mm. So this is the average diameter. And now first of all we will find out the spindle speed for the very first pass. So let us find out the value of spindle speed for the very first pass. We will write here that N1, that means spindle speed for the first pass, is equal to 20 cross 1000 divided by pi into 37. Now let us solve this equation. The value of n is 20 cross 1000 divided by 3.14 divided by 37. That's equal to 172.14. 172.14 RPM. This is revolution per minute. What is the machining time equation in turning? What is the machining time equation in turning? The equation of machining time in turning is very simple. Machining time equation for turning is L effective upon Fn, where L effective is nothing but length of the workpiece plus allowance, and in allowance you can add all those length of approach, length of over travel, all those things can be added. So here you can write LO plus LA. Now LO means over travel length and LA means approach length. Okay, feed, that will be in mm per revolution, and RPM, N is spindle speed, that is revolution per minute. So the length will be in mm and the other feed will be in mm per revolution and RPM will be in revolution per minute. So here if we multiply feed with RPM, so we get mm per revolution multiplied by revolution per minute. So revolution gets nullified, and mm per minute is the feed velocity. Mm per minute is the feed velocity, right? In machining time calculation, we don't place cutting velocity at the denominators, rather we go for feed velocity, right? Now, machining time, what is the length in the first pass? In the first pass, we will reduce the entire 100 mm down to 34 mm. We are going to reduce entire length of 100 mm down to 34 mm. So in machining time calculation, we'll place here 100 divided by feed value is 1, and RPM that we have obtained was around 172.14. 172.14. So this will be in minutes, and that is the machining time for the first pass. So 100 divided by 172.14, that's 0.58 minutes. 0.58 minute. Now this is the time for the first pass. This is the time for the first pass. This is time for first pass. Okay, what next? Then we have to go for the second pass. The second pass will involve only for the rest 60 mm, because this 40 mm is already done after being converted down to 34 mm. So if we have this 40 mm length converted to 34 mm dia, so we don't need any further machining here. We don't need any further machining in this section. Rather, if you want to go for the machining, it has to be for the rest 60 mm length. It has to be for the rest 60 mm length. Okay. So now let us focus on this 60 mm. In this 60 mm, we have to convert the diameter to 26 mm. We have to convert it down to 26 mm. So let me check the question. Yes. How to convert into 26 mm diameter from 34? We have a depth of cut of 3 mm. Depth of cut is of 3 mm. So when the depth of cut is of 3 mm, the reduction will be of 6 mm. The reduction will be of 6 mm, because we all know that depth of cut is a radial reduction in the cylindrical workpiece. Okay. So when depth of cut is 3, the reduction will be 6. And can you tell me what will be the final diameter? Because right now, after first pass, the initial diameter is 34. So we can reduce down to 28. From 34 to 28, we can land in the second pass. So our all calculations will be now for the second pass. So I will write here second pass. I'll write here second pass. In second pass, the value of n is V. What is cutting speed? That is 20 cross 1000 divided by pi. What will be the average dia? 34 and 28. The average dia will be 31. So now let's go for the calculation of the spindle speed for the second pass. So you can see that for every given pass, we are calculating the spindle speed. So whenever the cutting speed is given to you, you have to go for this exercise. You have to calculate the spindle speed for every pass. So right now 205.35 rpm is the spindle speed. What next? We will place the equation of machining time for the second pass. This time the length will be only 60 mm. The feed remains as 1 mm per revolution, 205.35. So 60 divided by 205.35 is equal to 0.29, 0.29 minutes. 0.29 minutes. Okay, fine. Now we have to go for the third pass. This is the time for the second pass. In the third pass, we have to reduce the diameter from 28 to 26. So this time we will keep the depth of cut as 1 because now the reduction required is only 2 mm. So we will keep the depth of cut as 1. In the previous pass, I mean the second pass, the depth of cut required was the maximum one up to 3 mm because we wanted to reach from 34 to 28. That was our maximum reduction possible. So from 34 mm to 28 mm we have taken the depth of cut as 3, but since from 28 to 26 requires a reduction of only 2 mm, we have to take the depth of cut only as 1 mm. So now let's go for the third pass. Let's go for the third pass, or I'll keep it here and then I'll go for the third pass. So I'll write here third pass. So already the cylindrical body has a diameter of 34 mm for a length of 40 mm, and for the rest 60 mm we have already reached to 28, but now we want it to be 26. Okay, and it is slightly greater than 26, that is 28. So n, calculation of n is very important. So for every pass the calculation of spindle speed has to be there. Average dia will be 27. Okay, because third pass we are reducing the diameter from 28 to 26, so the average dia will be 27. So now let's go for the calculation. 20 divided by 27. Well, 20 divided by 27 into 318.3, that's equal to 235.777, 235.78 rpm. Now what would be the time for the third pass? T3, length remains as 60 mm, divided by feed is 1, 235.78 rpm. So 60 divided by 235.78, that's equal to 0.25 minutes. So 0.25 minutes is the machining time. 0.25 minutes is the machining time. Okay, so now we are done with the total machining. So the first machining time was equivalent to 0.58, then it is 0.29 minutes, and then we have 0.25 minutes. So total time of machining is equal to 0.58 plus 0.29 plus 0.25. Okay, so it's 0.29 and 0.25, so it's 0.54, and from here we have 0.58, so it is 1.12 minutes. So this is the machining time, this is the total machining time. So what is the main point that you get from here? That whenever cutting speed is given to you, you have to calculate the spindle speed for every given pass. So you will make it a note statement, you'll make it a note condition that if cutting speed is given to us, then we need to calculate spindle speed. Calculate spindle speed step by step, or we can say pass by pass. So we can calculate the spindle speed for every given pass if we have the cutting speed given in the question. So this is the point that we wanted to draw here. If a spindle speed is directly given to you, let's say we have a condition that we need to reduce down the diameter from 60 to 54 mm and depth of cut is 2 mm. Let's say depth of cut is 2 mm. Okay, and feed is given to you as 1 mm per revolution, and spindle speed is also given to you as 200 rpm. Now you need to find out the machining time. Now this is another case that I have provided to you. So let me come down to the next page. Okay, just look at this condition. We have a length of 60 mm and a diameter of 60 mm. We need to reduce down the diameter from 60 to 54. We have to reduce on the diameter from 60 to 54, and the depth of cut given to us is 2 mm. So you will say, sir, depth of cut is not sufficient. Yes, I know depth of cut is not sufficient, because if the depth of cut would have been 3 mm, we could have got a reduction of 6 mm and the diameter would have reduced from 60 to 54. But right now the depth of cut is only 2 mm. That means we will have to go for some passes, more than one pass. So in the first pass we will be able to reduce down the diameter from 60 to 56 mm, because the depth of cut introduced cannot exceed 2 mm. When the depth of cut is given to you in the question, it means maximum penetration. It means maximum penetration. Okay. Now the second pass requires diameter reduction from 56 to 54. So this time the depth of cut will be only 1 mm, because the total reduction is 2 mm. So depth of cut is 1 mm now. So here, since spindle speed is already given to us, we don't need to calculate spindle speed for every pass. Rather, the machining time equation will be L effective upon Fn into number of pass. So this N is number of pass. So when spindle speed is given to you in the question, you can directly multiply by the number of pass, because when spindle speed is given in the question, that means for every pass, the spindle speed is going to remain constant at 200 rpm. So L effective 60, feed is 1, rpm is 200, and number of pass is equal to 2. Number of pass is equal to 2. First pass we get a reduction of 4 mm, so we land to 56, and the second pass we get a reduction of 2 mm by keeping the depth of cut only 1. We don't require 2 mm as our depth of cut in the second pass. So now we can easily go for the calculation. 60 divided by 100 is 0.6 minutes. Okay, so 0.6 minutes is the answer. This is the total time required for both the passes. So another node condition appears here. It says that if spindle speed is given to us in the question, then machining time equation is L effective upon Fn into number of pass, and this number of pass depends on depth of cut. It depends on depth of cut, right? If in this very question depth of cut would have been say 1 mm, if the depth of cut would have been 3 mm, then you would not go for 2 passes, rather single pass will be enough for this case. If the depth of cut is 3 mm in this question, then we can immediately jump from 60 to 54 in one pass only, right? So here we have another node condition that if spindle speed is given, then apply LE upon Fn into number of pass, and number of pass depends on depth of cut, right? Okay, so I hope you have understood this very case of turning, where in the first case I gave you the cutting speed, in the second case I gave you the spindle speed in the question, right?